It's actually a little process. I had to fuzz the background. You can see the background really sharp. Okay, so it's 7:30 and we're going to get started. Welcome to the June meeting of the Johnson Space and Astronomical Society. We're going to get started. There's Stan up there. This is Stan's picture of Comet. Tell us what that is, Stan. Yes, there you go. So what we're doing is if you guys have a picture you'd like to have on the first slide of our meetings, let me know your picture. People like Phil and others that have a picture like that. And we'll put your picture on the front slide. That's something new we're going to start doing. Anybody that does astrophotography. Thank you for contributing that, Stan. All right, here's our agenda for this evening. Now, well, you're just going to have to listen better or come down here because this is as loud as it gets. There's a microphone right here. It's not, I don't know why it's not turned on. Well, why don't you move down here? You can hear me better. Let's see. How do you like that? I figured it out. Okay, so if this is your first time here, we'd like for you to raise your hand, tell us your name, how you found out about the JSC Astronomical Society, and what your interest is in astronomy. Anybody first time here? Right there.
I'm Bianca. I have the app Meetup, and I saw this was on there, and I thought, awesome, I'd love to come. I've always been interested in astronomy, just kind of a hobby. You know, I love the stars, love the planets.
Great.
I just thought I'd like to learn more. Here I am.
You came to the right place. Anybody else? I know there's some other new people here. I'm not going to embarrass you guys. I know I hate it when people do this to me, so I won't do it to you. Right there.
Hello, everyone. I'm Desmond, interning at JSC Procedures Management, and I found out about this event through a resident at Hunter Club.
Is that Austin by any chance?
Yes, it is Austin.
Austin! All right, so Austin gets 1 brownie point. All right, anybody else that wants to admit that this is their first time here? Anybody? Okay, you guys.
Hi, I'm Tegan. I'm also a new intern at JSC. I'm in EP4, the Propulsion and Power Division. And I also found about this meeting through Austin. Yeah.
Okay, 2 for Austin. Are you with Austin also?
3
for Austin. Okay, what's your name?
Hello, I'm an international intern at JSC. I come from Sweden, so I'm represented by the Swedish Space Agency. Yes, I'm looking forward to seeing what it's all about. And of course, I love astronomy. Otherwise, why would I do?
Excellent. Very good. Thank you. I'm glad you guys are here. Anybody else first time here? Okay, Austin got 3. That's really good. I know you guys are new up there, but I'm not going to embarrass you, even though I already have by saying that. Okay, let's see. Are you doing questions or not, Trevor? No. Okay, forget that then.
You have my laptop.
Yeah, I see that. We're using Trevor's laptop to run the stream now, so we're limited in what we can do. And thank you again, Trevor. He's the guy that makes the stream work. We get about 100 to 200 people actually watch this meeting every month on the stream. So great that you guys are all here, but we also got a big online audience too. Thanks to Trevor. He's really the one that made all that possible. Okay, so many of you have asked me about getting on the email distribution list when you were coming in. But if you're not getting our emails and you want to Al is holding up a clipboard back there and it has these little tear-offs. And there's two kinds of meetings. One's meetings only, one is everything. And you can send your email address to that. You can tear off one of those, send your email address to that, and you'll get on our distribution. Or if you want to take a picture of this, you can send your email to one of those two. One's meetings only, and one's everything. And then you'll know everything that our organization is doing. Okay, so speakers, remember to please use the mouse pointer here so the online listeners can see what you're pointing at. And this Mac, the mic for the stream is actually in the laptop, and the mic for the room, people were complaining they couldn't hear us a minute ago, so turn the mic on, Trevor, is here. So you're gonna need to be kind of in this general area. I know some people like to walk all over the place, but if you walk over there, nobody's gonna be able to hear you on the stream. So you need to kind of stay in the general area of the laptop when you're doing your presentations. All righty. I feel like I forgot something, but I don't know what it is. It's okay. So our main speaker tonight is Dr. Brandon Riddell. And before he does his talk, I'm going to tell you a little bit about him. Brandon Riddell currently works at NASA in the engineering directorate and focuses on space radiation environments and their effects to space vehicles and hardware, which he has been doing for most of his career. His background is in space physics, particularly in the area of high energy collisions involving galactic cosmic radiation. He received his master's in applied physics from Johns Hopkins and PhD in physics from the University of Houston. Brandon is currently a member of the JSC and has been an amateur astronomer for most of his life and enjoys attending star parties too. Also, Brandon actually is a professor, astronomy professor, I believe. He left that out. He's a modest guy, but he also does that too. So.
Thank you.
Okay, so.
All righty. Glad you got the mic working. Hopefully you guys can hear me in the back. Yeah, my pleasure being here. Yeah, as we said, I've been a member here for quite a while, but I haven't done a talk in so much time, right? So tonight I want to talk to you about our unique position in the solar system. This is really a part 3 of a couple of talks that I gave pre-pandemic. If you remember, some of you may have been here when I talked about the like conditions for habitability, not only from like here on the planet Earth, but like what about in our solar system and then in our galaxy. And so what I have tonight is it's a little bit of an eclectic talk. So just bear with me. I want to kind of build up some motivation and really just talk about some research that I through the photography that I've been doing. I've been thinking about stuff with globular clusters and then looking at what that means in the long run with some of the elemental abundances that we see here on Earth. And so let's see here. Okay. All right. So here's sort of the outline of my talk, right? And so I mentioned I really need to kind of set it up, and because I said it's eclectic, right? There's a lot of fields. Of course, I'm not an expertise in all of these, but there's some geology and things like that in here. But I want to talk about the review of the habitability, just to say that we're kind of on the same page on where I'm coming from with the background here. And in particular, I'm focusing on the co-rotation radius, and I'll explain that here in a little bit. A little bit on star clusters. I'll show some of my very short duration images, not many. And then talk about elemental abundances and what we see that's really unique here on Earth and really our solar system. And then I'll talk a little bit about some of the research on some of the oldest material in the solar system, which are called pre-solar grains, just dust in our solar system. And then really number 3 there, that's the paper that came out last year that I want to kind of talk to about some modeling that really shows some unique things that might explain some of these elemental abundances that we're going to talk about. And so kind of going back, this is one of my conclusion charts. I think I did this back in 2018. And so, as you know, like with James Webb and a lot of ground-based astronomy and really like Kepler telescope, the TESS satellite, right? Planetary exoplanet research, planetary habitability is really a thriving area of astronomy. It's growing and it's exciting. But we always hear about the habitability being in the water zone. And what I tried to show you that there's a lot more than just being in the water zone, right? And so what we mean by that is being in the Goldilocks zone, right? If you're too close to the sun, right, you get too much solar energy, and depending on your atmosphere, you can have the greenhouse effect, and basically have a 800-degree planet like we have with Venus. And then if you're too far, right, it's the opposite side, and we could have there's different terms for it, but basically a frozen planet or a frozen world. And Mars is just outside the habitable zone in our solar system. Now, what comes with that, just from water alone, is certainly a prerequisite, but there's all these other things. Ultraviolet light, right? People don't think about that, but if you have too much ultraviolet light, that's needed. If you have too much, it can break apart DNA, basically, right? But if you have too little, we actually need that energy source in a lot of life-critical compounds. When we talk about photosynthesis, again, being at the right distance from the sun, in addition to being in the water zone, in addition to being in this sort of ultraviolet zone, and some of the other ones here, obliquity and tidal, right? So some of these need combinations of things. But you can't have photosynthesis if you don't have all these conditions. Ozone, right? My throat's a little bit hoarse today because of the bad ozone here in Houston, right? The ground level ozone. But ozone is really important in our atmosphere. It assumes there's oxygen in the planet, and it's O3 in our atmosphere, and that shields 95 or 97% of our shortwave UV light from reaching the ground, which protects, has critical impacts for life as well. And then I'm kind of looking at my notes because it's been a while. Planetary rotation rate. When we look at exoplanets, we don't have the technology to understand how fast they're rotating, right? Or the obliquity, and I'll talk about that here in a second. But obviously that affects cloud cover, circulation, right? It's balancing the stellar radiation coming in from the star. The higher the rotation rate basically pushes both the water and the UV zones outwards, and also the ozone, consequently the ozone as well. And so you have to factor those things in. And then likewise obliquity, right? That's the tilt, right? We're tilted 23.5 degrees. The obliquity affects how oceans warm, how continents cool. And again, the higher the obliquity, the further out the habitable zone comes. And then what we see with tidal zone, right? Tidal locking. You guys might be familiar with the fact that the moon faces Earth, right? The same face. It's tidally locked with the Earth. And so 76% of the stars on the main sequence are M-dwarf planets. And so what you're seeing, you may have seen this with all these habitable planets that we're finding around M-dwarfs, because the stars are so small, all these planetary systems are, have like 9-day periods around the star, right? And so most of those are so close that they're probably tidally locked. And that causes big problems because you have the front side facing the star, hundreds of degrees hotter than the backside. And not to mention what that might do with planetary circulation and so forth. And then you have these sort of more larger scale structures. The astrosphere, you could look at that as also the heliosphere. There's some fine structure there with how that forms inside the molecular clouds. And then we also have the electric fields. There was a couple papers recently at the time, a few years ago. When you have ultraviolet light coming from the sun, it dissociates, let's say, oxygen or nitrogen, whatever your atmosphere is. And because the solar wind, like electrons are 1,000 times lighter than the protons, right? They get separated and you get electric fields set up, and then they can actually accelerate the loss of planetary atmospheres. And so those are all big issues. And then finally, I talked about space weather effects. Again, M-dwarf stars, 96% of the stars are M-dwarfs, and they're 100 to 1,000 times more active solar storms. And so there's several papers out there that talk about problems with retaining planetary atmospheres for those kind of stars. Yeah.
So you're going to say more about liquidity later?
I did. I'm just kind of summarizing what I did before, but what I was trying to say is the tilt, right? I mentioned this a few seconds ago. Yeah, yeah. It has to do, so we'll have to go back to my other paper, but when you look at the research that was done, it's sort of a fine balance between the solar heating, right? There's different thermal capacities in the ocean than there is in land. And so based on that heating distribution and the land mass, whatever the ratio is, that affect the global effect for the heating of the planet depends on those ratios and the obliquity. And so what they find is when you go further, more oblique, right, it basically affects the overall weather patterns such that with like cloud cover and so forth. And that
further out.
Yeah.
Okay.
Yeah.
Okay.
Yeah. So my whole point here is just to tell you there's a lot of factors other than just water. Now, stepping back to a larger scale here, let's look at even the galactic considerations. And this was really the part 2 of the talk that I did a few years back. And so it's kind of like the Goldilocks zone again, but with all these other conditions. Galaxies must be in a stable location for billions of years. And what that means is isolated in an isolated supercluster. I'm not sure if you guys know, but our solar system is part of this local group of galaxies. And we're part of the Virgo cluster, which is a subset of this thing called the Laniakea cluster. And these are very large scale structures in our universe. And we're actually kind of on the side and away from all this activity of perturbations from nearby galaxies and so forth. So that plays into this idea of the right local neighborhood. You want to have a low number of large galaxies near us, large separation between all the individual ones, right, to minimize interaction times on the scales needed for life, for life to develop and so forth. You also need a lot of close by dwarf galaxies like we have in our Milky Way, right? Dwarf galaxies eventually merge into the main galaxies and provide a lot of the dust and gases which are condensed and form stars eventually. And then there's the whole idea of the right type of galaxy. In astronomy, galaxies are pretty much classified into irregular, elliptical, and spiral. So elliptical and irregular types are not good candidates. And in my talk, I spent a lot of time talking about why, but it really comes down to you can't have stable solar systems for long periods of time because you have chaotic orbits, right? You have elliptical type galaxies have very, and I'll use this term metallicity, and I'll define that here in a minute, but you need elements to form planets, and a lot of the stars and the gases in there are just too old and don't have the right elemental abundances to support planetary formation. And then what I have here circled, again, this was a chart that I showed before, but this is really kind of the takeaway from this one slide that we need to think about for my talk tonight. That is our location in the galaxy. We actually our solar system is near the co-rotation radius, and we're in between spiral arms, and that's important. So what is the co-rotation radius? It's the distance from the center of the galaxy that a star revolves around the galactic center at the same rate as the spiral arms. And so this is just an image, right? It's an artistic image because we can't image our Milky Way from above, but this is what we think it looks like, and that black circle there is representing the co-rotation radius. It's about close to 8 kiloparsecs from the center. I think we're 26,000 light years from the center. Now, just like planets rotate around the star, like our sun, our solar system rotates around the galactic core. And that's all determined through Newton's laws of motion. It's pretty regular motion. But this idea of how the spiral arms work, actually have a typo here. It's density waves, plural. Density waves determine the rotation rate of the spiral arms, and it has to do with not only do you have physical objects moving around the core, but you have pressure and gases that get bunched up at various times around the orbit. And so it produces these waves, and that's what drives the rotation, the actual spiral arm structure, while you still have the material rotating around the core from a physical standpoint. And so if the Milky Way galaxy is much larger, the co-rotation radius will be further out. And that's a problem because the further out you are, you have less exposure to all the nearby stars, which are needed over the lifetime of the galaxy to produce the kind of elements you need to have planets and other stars. And then if you're too close, right, not only do you have gravitational problems and instabilities, you're also moving faster than the spiral arms. So the solar system's actually rotating faster through the spiral arms. And so we're moving through thick molecular clouds and dust and other nearby stars, which would disrupt the solar system, our solar system. And then, so right here is showing the same image on the top right with the co-rotation radius. From the paper I've listed there, so metallicity in astronomy is it's simply all the elements on the periodic table of elements heavier than hydrogen and helium, right? You have the light elements, hydrogen, helium, and everything else are called metals. So, and those are heavily studied in all areas of astronomy to identify processes and things like that going on. And so when you look at the metallicity working from the core of our galaxy outwards, that's what that bottom right graph is showing. And so at the co-rotation radius of around 7.8 to 8 kiloparsecs, our location, there's like a local minimum there. So the metallicity, you have that very large bump. Let's see if I can use my cursor here. Yeah, we have this high metallicity region here, and we're in this region right here. And it effectively drops off as you move out to the edge of the galaxy. And so let's see here. So spiral arms contain not only giant stars, right? A lot of molecular clouds and dust, star-forming nebula. Like you'll see a lot of kind of blue. When you look at people's galaxies, you'll see star formation regions, and they look like little blue gaseous kind of regions in the galaxy arms. Those things are all producing from the stars radiation, and so you know if you're near the center of these arms, you're not only exposed to deadly radiation, you're also exposed to the gravitational perturbations, right? Just think about a star sweeping through our solar system, right? That's going to disrupt the planetary motions. A star's right at the co-rotation radius, right? If we're exactly, let's say that's actually it, that white line, a circle. If we're exactly at that, just like we see in our solar system, there's something called mean motion resonances, and those have to do with the gravitational interactions coming from above and beyond, and eventually it becomes unstable and can be kicked out. And so we're actually just inside the co-rotation radius. Now, this is the second or third piece of sort of background information. Now, it doesn't look really good here, but some of you may know that from the recent astronomy trips, I've been sort of taking images of going through all the catalogs. I'm seeing a lot of galaxies, and there's tons of clusters. I think there's actually, I tried to look it up, I think there's 155 to 160 globular clusters in our galaxy. Now all of these images here, I kind of made a collage out of them, and some of them are out of focus because they're really small and I had to zoom in on using a low res photo. The point is, they have all sorts of shapes and sizes, a number of stars in them. Some are open clusters, and then some are globular clusters that look like balls. And so that got me to think, because when we look at our Milky Way galaxy, again, the left image here is like a top view. But if you look at it edge on, you see more of a distribution of the globular clusters. A lot of them are in the disk, but then a lot of them are in the galactic halo above the plane of the Milky Way. And so I already knew in my mind that there's a lot of people that think most stars originate from clusters, right? And because of gravitational interactions, they can be kicked out and so forth. And so that kind of got me thinking about where, how do we explain like the high metallicity count, right? There's a lot of evidence that says maybe our solar system formed closer in than where it is now. And so some of that evidence comes from the abundance of elements. Now I have a list here. This is not all inclusive, but we have to sort of anchor this to sort of the average abundance of the Milky Way galaxy. And we do that by referencing it through magnesium, because magnesium there's a couple papers out there that show it's very similar to what we have in our solar system. And so assuming that that's, it's fairly sort of like a metric we can use. When you actually look at Earth, like our crust, right, we see 40 times more aluminum. We see, I'm not going to read through all these, but the key ones that I'm going to talk about later, like uranium and thorium in our core are hundreds of times above the Milky Way average. And so one might want to think, well, how does that play into planetary processes and so forth? And I'll talk about that. And then I kind of separated up these bunches here on the right side, and I'll talk a little bit about those more later, but those are what we call vital poisons, right? All of these are critical for life functions, and it's one of those things, too much or too little, it's bad, right? It has to be just the right amount. Now, one more thing here before we kind of look at this other paper I want to talk about. So the majority of stars in our galaxy are formed from clusters of at least 100 or more stars. This was from 2003. So this is still active research because the numbers have been changing, but for a long time now, we've known that most of the stars are formed from clusters, and then the clusters eventually break up. Now, there are 3 different observations, and probably more, that convince most astronomers that the solar system was formed from a cluster of at a minimum of 500 stars. And there's all sorts of multi-body physics problems looking at star cluster interaction, right? And trying to understand these chaotic motions of these trans-Neptunian objects. They're like, asteroids or comets maybe out way beyond Neptune that have really odd orbits that are very highly elliptical, and they can't be explained from solar system model formations. And so the idea is if they interacted with other star systems, that could help explain some of the weird orbital parameters they have. And then the bottom 2, it looks like some of the formatting's there, but number 2 and 3 there, isotopic composition of pre-solar grains is really a lot of the focus today is in trying to understand the origins of our solar system. Again, pre-solar grains are just the dust particles that are present, and usually they find them, looking at them in meteorites, but those are the oldest materials we have in our solar system that we can study, and we have a lot of data on those. And so there's several papers out there, and I'm going to talk about these here in a minute, that try to show that through close and nearby core collapse supernova, right? The normal idea of a supernova, right? A star blowing up, sending out all these elements, somehow infused into our solar system at an early time. And so that's what kind of these last 2 papers are here talking about. And so the first one, this is from 2016 in the Annual Review of Astronomy and Astrophysics. It's actually a pretty interesting paper because it covers more than just this one topic. It has quite a bit. But what Larry Nittler and them, this is sort of a summary from the paper. Isotopic composition of pre-solar grains differ from the sun's current position, right? The isotopes, we're talking about radioactive elements, or, like now we have the daughter products that we can see, but earlier times we had more like radioactive elements. Extinct radioactivity suggests the sun's birth environment was decoupled from the average nucleosynthesis for tens of thousands of years, millions of years, but was enriched in short-lived isotopes from massive stellar winds from AGB stars, and I'll talk about those here in a second, or explosions. And what do we mean here are supernova, core collapse supernova are just type 2 supernova, the regular type of supernova that we all understand, basically. But these things happened early on in the solar system formation. Now, these were, looks like, so this right plot looks like it's at the duplicate. Really, there's just these two plots here on the left. Now, this, hopefully you can read that, but what it's showing is, this is from that paper I just showed. Now, the takeaway here is the red squares that are kind of in the center. Now, these are plots. The left one is the ratio of two oxygen isotope ratios, right? One ratio versus on the x-axis, the oxygen 18 and 16 ratio. And so what they do is they plot all these samples that we get from the solar system, and then they also calculate a bunch because we're given certain stellar processes, types of stars, right? They have different kind of nuclear physics going on. You can actually calculate and predict the type of elements you would see in a solar system formation type model. And so both of these show, it's harder to see on the left one, but on the right, which is the ratio of nitrogen and carbon, these red dots right here are actual samples from our solar system, from meteorites. And it falls in this bubble here that says AGB stars. And so their conclusion, there's a lot more to it than this. I'm just summarizing it. But the majority of the oxygen-rich and carbon-rich pre-solar grains in our extraterrestrial materials are believed to have originated in the AGB branch stars, low to intermediate mass, 1 to 8 solar masses. Early, the key thing is, stars in very late. The stars that produce those were in their late stages, but they were those same elements show up early in our solar system formation. Now, you may ask what an AGB star is. So just as a little bit of a sidebar here, this diagram is very simple right now, but this is known as the Hertzsprung-Russell diagram. We often show this in astronomy, and it's simply a plot of luminosity, which is the energy output of a star, right? Amount of ergs per seconds, whatever units you want, but it's the energy per unit time relative to the sun versus temperature. And just note that the temperature is always flipped on this, right? It goes from high to low temperature. And so our sun here is right here where my circle is, my mouse pointer. The main sequence, so if you were to look at every star that's out there in its normal hydrogen burning phase, it would plot based on its brightness, its luminosity, and its temperature. It would fall on this curve here that says the main sequence. Now, towards the end of the life of a star like our sun, right, once we burn all of our hydrogen, while it's fusing hydrogen, it's producing helium, and that's heavier than hydrogen. It starts collecting in the core, and what happens is it comes off this main sequence when it's starting to die, and it's trying to burn hydrogen like out in higher shells, not in the core. And you have the temperature is not quite high enough to do helium fusion, but as you burn more and more helium in the atmosphere of the star, right, it's kind of collecting in the core, and eventually the core gets hot enough because of gravitational attraction to kick off helium fusion, which is sometimes it's fusing into carbon through the triple alpha process. But this point right here, they call that the helium flash. And then basically what happens, it actually kicks off the helium fusion, which heats up more, right? So the temperature kind of comes up, and the star actually changes its diameter, and that affects the luminosity. Anyways, it comes back down, and then you have the same process over again, but with relative to helium, and then it starts coming along this branch here, and this is what they call the asymptotic giant branch, because it's basically in a similar shape to the this red giant branch here. This particular diagram kind of has it exaggerated a little bit, but the point I'm trying to show you here is where these AGB stars are kind of late in the star cycles. And what's important about them is they're known to have very high, they have very high mass loss, right? It's well known that they have very high solar winds or stellar winds coming from them. And so, anyways, and then like for our sun, eventually it comes up here and then it kind of stabilizes and the path would come all the way up here and then it'd end down here in a white dwarf phase. So that's what an AGB star is. And then one other paper, again, this is from 2009. I just wanted to bring out, because I haven't talked about it, there are all sorts of elements infused in our solar system, but there's these things called short-lived radionuclides. And so here's a bunch of them. Now, this is not all of them, but 26 aluminum, that's the one I'm going to talk about tonight, that decays into normal aluminum that, we see all the time. In iron 60, that's another important one too. But all of these, we know were in the early solar system. And so this particular paper back in 2009 concludes that the intermediate mass AGB stars and massive stars in the range of 20 to 60 solar, somehow that got left off, but solar masses are plausible sources. So at the state of, 15 years ago, that's kind of where they're thinking. And so things have changed now. So this kind of gets to the point of this talk here, starting at this point now. So hopefully, I'm kind of all over the place, but hopefully you kind of understood a little bit what's going on. Now, last year, a couple of Japanese astronomers published this paper in Astronomy and Astrophysics, and it's titled "The Number of Stars in the Sun's Birth Revisited." I came across that and I was like, oh, wow, this is really exciting. We're talking about globular clusters. I've been imaging them and I understand these kind of concepts from habitability and trying to understand, where did all these interesting ratio of elements come from? Well, I mentioned looking at aluminum 26 is an important element. And so from their abstract here, they're looking at aluminum 26 and they're called CAIs, calcium and aluminum enriched inclusions, right? Those are just elements of calcium and aluminum in meteorites. Now, they claim here that there's a direct injection of aluminum 26 material from nearby core collapse supernovas, and they would expect that they had occurred in the first 100,000 years of the existence of our solar system. We find that the number of stars in the birth cluster may be significantly greater than previously considered, right? I don't know if you remember, but in one of the earlier papers I cited, they were saying, hey, it's at least 500. Well, we'll see here what they're trying to calculate. And so this is just a schematic that kind of outlines their modeling. Now, if you work your way from the bottom up, let's say, so starting with this black line right here, TSF is the time frame for star formation, and that could be anywhere from 5 million years to 10 million years. And there's a lot of debate on that. And it really depends on the type of star you have, really the cluster you're in, and where are you inside the galaxy. And so there's sort of a range on that. But it seems like it's converging closer to the lower side of 5 to 7 million years from what I've seen. And so the idea is you have some cluster that formed. Now, if you remember from previous talks, when you have an interstellar cloud, you get a perturbation in it. And once you get a star moving, right, its gravitational attraction pulls other stars near it. And this is how a single star forms too, right? You just get gravity kind of works on all these things together. And so at this point in some cluster somewhere, let's say our solar system birth cluster, we have several stars that are like solar type stars. And we also were nearby some kind of massive star, right? We don't know how far, but it's assumed that there's at least one. And so what happens is in their model, they predict that, okay, this massive stars go through core collapse supernova, right? A type 2 supernova. And that just so happens to happen in around the first 100,000 years of when this green line is the formation of our solar system, really the formation of our sun, and then everything else around it. And so they created a model and did a lot of simulations. And this is taken directly from their paper. This is sort of the main results they're getting. And so they're saying that the probability of the direct injection of short-lived radioisotopes, SLRs, from core collapse supernova is 50%, and the initial size of the birth cluster is 20,000 stars. And so you can see that from this graph here, right? If you have about 20,000 stars, go up to the blue line, which is the star formation assumption of 5 million years, you get a probability of that happening of 50%. And this right graph here is just a different way of representing the same data. And so their conclusions are, there's a lot more to it than this. I'm just kind of giving you the high level one. Injection of aluminum-26 materials in the solar system from nearby core collapse supernova must have occurred within the first 100,000 years, and that to explain the amount of aluminum-26 injected in the solar system, the star became the star that actually blew up had to have been between 20 and 60 times the mass of the sun. And so that's kind of their conclusion. Now, you may be wondering why the heck am I even thinking about these things, or why is this even important? This particular paper, looking at the idea of short-lived radioisotopes, again, this is a quote from the paper, but the fact that they're present has ramifications not only for understanding our solar system, but any solar system as we do exoplanet research. What they concluded is the rapid decay and high abundance of aluminum-26 produces enough heat to melt and differentiate planetesimals at early times. Such radiogenic heating may significantly move the snow line outwards, right? That I was telling you about the habitable zones, like the line that, there's like a range of good temperatures where we have liquid water. The one that's furthest away from the sun, like Mars, is just outside that snow line, right? Early in the solar system, these factors play an important role, right? The aluminum-26 is radioactive. It decays into aluminum-27. It's emitting a lot of energy that heats and it controls how much water is formed in the early solar system. And so that's what that last bullet's trying to say. And they've actually said this in the paper, that this is important for technological civilizations, right? The amount of water you have in a solar system, right? Too much, right, is not good.
Can I ask you a question?
Yes.
I read this one, that too much water, despite like intelligent dolphins and all that, they never will develop or work on material science. They don't have fire.
Oh,
You cannot make,
right.
you cannot melt materials, combine materials.
Yeah.
You cannot make fire. So that alone is prohibited.
Yep. Yeah.
No matter how intelligent they are.
Right. And I think that's, so for the people I'm not sure if they heard that. They can't hear that, right?
Maybe.
I'll just repeat it. But yeah, gentleman here's telling us that he had heard in the past, make sure I'm stating it right, but like if you had just a water planet with aquatic species of any kind, right, there's no ability to generate tools or fire and things like that. And potentially, I mean, it's hard to say like in the end, how things would be, but that certainly would make sense and consistent with this claim they're making in this paper. And then just really quick, going back to the aluminum-26 idea. Again, this is from around 2009 also. I just wanted to point out, even back then, they recognize with the best of solar system formation models that they could not generate from our sun alone the right ratio of aluminum-26 to 27, right? They said right here, it's difficult to produce in models of star formation. So that, and along with observations of metallicity and other things, is sort of the motivating factor about the thinking that our solar system probably formed closer in. And then they said, we suggest that volatile loss of heating of planetesimals favors future development of technological civilizations in solar systems with elevated concentrations of aluminum-26. All right. So going back to this chart I showed earlier, I mentioned uranium and thorium. Now, I'm not going to go into all this in this particular presentation, but I do want to talk about plate tectonics here in a minute. So uranium and thorium are radioactive elements, and we have a lot of it in our core, right? We have a liquid iron core. So these elements are responsible for generating heat to keep it in a kind of a pseudo fluid state. And it's only because it's in that state that we have a stable magnetic field, right? Think about that. Our magnetic field is very stable. Jupiter is the only other planet that sort of has a liquid core too. Very stable magnetic fields. And that certainly, as we all know, affects habitability. But what a lot of people don't know, and that's what I want to talk about here, is one application before I conclude, is that it has a super important impact on plate tectonic activity. And then finally, I think I mentioned this earlier, all these things on the right here are vital poisons for life, right? All these elements are necessary for life. You could spend, each one of these could be their own paper to understand here. So what is it about uranium and thorium? So has any of you ever heard of the carbonate silicate process? Okay, we got one, at least one. Okay, so when we're talking about habitability, it's pretty well documented, and sorry I don't have it in this pitch, but if the solar luminosity, our sun's luminosity was either 2 to 4%, either higher or lower, we would either be in a greenhouse state or like Mars, right? A very cold planet with a very thin atmosphere and so forth. The other fact is we also know that our sun, right, as we move through the hydrogen burning phase, and eventually we're going to start burning helium, right, it's always going to get brighter. And so we know that our sun was 20% less bright 4 billion years ago, right? The age of the Earth is about 4.5 billion years. So the question is, throughout all of life's history, the sun increased 20%. So what is the control mechanism that kept us from not turning into a greenhouse type of planet or a ice planet, right? There had to be a compensating factor because the sun, we know the sun's changed by 20%. And we also know 2 to 4% will push us outside those habitable zones. And so, and if you don't believe me, look this up. It's called the carbonate silicate process. Now, this is a geologic process, but it involves our atmosphere and plate tectonics. And again, this is operating over geologic time. It takes a long time for this to work. But what happens is the early Earth had a lot of carbon dioxide. And so if the sun's getting brighter, right, as it's, as it's getting into its nuclear phase, it's generating a lot more heat, right? The luminosity is going up. And so if you have all this carbon in there, that's a greenhouse gas. That's going to heat up the planet. So we need something to take the carbon out. And so that's what this process is doing. On the right side is sort of in words how the process works. Carbon dioxide dissolves in rainwater. All right, so you have to have rain. For forming carbonic acid, which interacts with silicate rocks, which creates calcium and magnesium ions, and then carbonic acid and or HCO3 and sand, believe it or not. So those products, through weathering and other processes, right, even life, the actions of life on the planet can affect some of this. These products eventually make their way to the ocean. Organisms make shells out of, let's say, the calcium carbonates, and then they die eventually, and they fall down to the seafloor and they get buried in the sediments, and eventually they get moved to plate boundaries where they're subducted. All that carbon's pulled down in there, and then depending on the volcanic activity and how it's linked underneath, some of it's sort of redistributed up through volcanoes, but a lot of it goes down into the core of the Earth where it's melted permanently. And so when we're talking about aluminum, the abundance of aluminum is about 40 times higher in our Earth's crust. What's helpful about that is that's actually facilitated this idea of the carbonate silicate process. And what I have here, this black arrow is pointing to, let's say, this plate boundary here. And so if you go look at that paper, but there's a compound called aluminous orthopyroxene, and it's a compound that has basically looks like sand, like silicon oxides, and it has aluminum in it. And what that does is that's a lubricating factor that's found only at these plate boundaries here. And so without the aluminum, you would not be able to. I mean, it's not saying it doesn't prevent the plates, but it allows it to happen more smoothly. Otherwise, you'd have a lot of friction there, and it wouldn't be an efficient process. And so, what they're finding out is that without this, it affects the scrub rate of carbon dioxide over the history of the life of the Earth. And so, this is a very important element, and it's something we find that's an abundant on Earth that we don't see in some of the other planets, right? And so, again, kind of going back to this idea of habitability, there's a whole bunch of things that affect what's considered for habitability. And so I just wanted to kind of point that out because it's a connection to really the birth of our solar system, where we came, how do we get the elements we have, and why, is there something special about that? And when we're looking for other planets, we should consider those sorts of things. And so I think got two more charts here and then I'm done. But so in conclusion, really what I tried to show you here is that our solar system lies safely right now near the Milky Way co-rotation radius, right? So we're at a safe distance from the core, away from a lot of the radiation, but we're at this co-rotation radius where we're not moving faster than the spiral arms, and they're not sweeping through us. So we have, for a long period of time, a stable solar system. The study of the Earth and the solar elemental abundances show that the Earth has a unique set of abundances. A lot of these are required for life, right? You change them, life might not exist. The solar system was not formed at its current location, but closer in. And that seems to be the general consensus, right? There's still more work to do there. And then research suggests that our solar system formed in a star cluster more than 500 stars, maybe as high as 20,000. And that can account for the anomalous orbits we see far out in our solar system. It also can explain the elemental abundances, especially in the short-lived radioisotopes. And so this infusion from nearby stars and of elements that are critical for life occurred early in the solar system. This particular paper, looking at the pre-solar grains, seems to point at this happened in the first 100,000 years. And then one particular example that I tried to show was this idea of uranium and thorium having several hundred times the average levels that you'd see in the Milky Way. And they're very important for things like magnetic fields or plate tectonics. And so finally, I just want to point out that that picture on the left, I took that off the internet. That's NGC 6139, a much better image than I took. But perhaps, that's a star cluster of about 20,000 stars. So potentially, if this is all right, our sun in the early formation days, we could have been in a cluster like this. And that's it. Thank you. Any questions? Yes, sir.
Very impressed. I've been following this for decades, with research and whatever comes out of it. If I add it all up, starting with page 9, with the galactic stuff, the galaxy, it seems like the Drake equation, and you revise it, life is kind of rare.
Yeah, I mean, I'm convinced of it now. Yeah. Well, I would just say, the Drake equation was formulated many years ago before we started finding out all these things, right? like the electric field thing, that only came out, that was a paper on a probe around Venus only in the last, I don't know, maybe the last decade. Yeah, there's a lot of factors. I think, life's complex. We should expect that there's a lot of complex factors needed to support it, right? And so I would just, when we're looking for habitability and like I didn't show it here, but in my pitch I did, I think it was 2018. I actually showed you articles where it'll say something like, "Oh, Earth 2.0 has been found," and then they show a picture, which we have no picture of any planet, but they'll show a picture with, you'll see mountains and a blue sky with a nice large moon, which I didn't even talk about here about our moon, right? Our moon relative to Earth is like, I don't know, compared to the next ratio, when you look at the size of the planet to the moon, it's a complete anomaly for Earth, our size of our moon. Well, just the size of it. And look at the importance, like why the moon's tidally locked and the impact it has on our tidal forces and things like that, right? And it's been stabilizing our Earth's spin axis and the obliquity. All that's controlled by our moon, right? So there's just a lot of factors, and it's like a can of worms. The more you kind of look into the research, the more questions open up, and it's actually pretty fascinating. But it touches all the fields of science, so it's pretty neat. Yes, sir.
So most of the things I've heard about the evolution of life on Earth, it didn't really start getting complex until this Cambrian explosion that happened like 600 to 700 million years ago. Is
Yeah.
that correlated to the motion of the Earth from its origin in the galaxy to its current location? Could it be where we were before was just prohibitive to multicellular life and just that bacteria for 2 billion years?
Well, that's so for the people in the net. I'll just repeat the question. You were asking about the Cambrian explosion, which is where we see like 3/4 of all the fossil skeletal structures that we see today kind of showing up, and how that correlates to where we may have been in the formation and like how I'm describing in this talk. Do I have that right?
Yeah.
So I haven't seen much on that, but I mean, that's certainly possible. But the one thing I would tell you is, there was something called the late heavy bombardment period that happened. So if the Earth's 4.5 billion years old, it was like a second round of like being pounded with like asteroids and comets from our formation of our solar system, right? All these rock bodies still out there, and it pretty much pulverized the planet. So there was like a magma ocean, probably, that most people think, from about 4.2 to about 3.8 billion years ago. And the oldest fossil evidence is like around 3.8, 3.6 billion years ago. And when I say fossil, I'm talking about like bacteria. And so we didn't have an oxygen planet at that time too. And so if you track the development of oxygen, how that's been, how did that ramp up over time? And the land mass, right? It was pretty much, if you look at the continental growth, right, it was very low, like less than 5%, and it grew up to the current values around 29% of the surface area. All that kind of gelled together. You needed a planet with oxygen to have all this life. So it's kind of funny how, you see this explosion of life happening right around when the Cambrian explosion was 540 million years ago, I think. And you see light, just an explosion of life happen right when the oxygen level gets to 18 to 20%, which is close to what we have today. And so I don't know how that correlates with where the solar system was. I don't think anybody really would have that information, and that's actually a good question. But I think once the sun's out on its own and the solar system's formed, right, it's its own machine, right? It's there's processes happening. We're controlled through the solar. The energy from a sun and so forth, right? And so everything's happening, on its own on Earth through the interactions with the sun. But we do know we didn't have any major interactions, so we couldn't have been near other stars. I think there's a few papers out there looking at supernovas. We've had a few early on that were close by that infused a lot of other isotopes as well. But we haven't had any in the last 500 million years or so that could impact the Earth, life on Earth. Yes, ma'am.
On the diagram up there, is the Milky Way, the bar, is that rotating clockwise? And does the sun stay on one of the arms, or does our sun have its own rate and actually stay on a circle of the red circle, or does it stay always embedded in the position and just move?
No. The sun rotates around the core. So we're in a barred spiral galaxy, so it kind of looks like a bar. And I think, yeah, in this image, if you were looking down from let's say like the north pole, the north galactic plane, right? I think that's rotating clockwise. I think that's right. Now the red circle is sort of just drawn on there, but it's estimated, that's about, given the width of the galaxy in that image, right? That's about a third of the way out, right? Which is around 8 kiloparsecs. Now, the sun, our solar system, we're not in the middle of one of these big arms. We're actually on the Orion spur, which it's hard to see in here, but in between this big arm here and this one, there's like a little bit of looks like a half arm. If you look it up, it's called the Orion spur, and we're just like on the edge of it. It's not a full arm. And so we're actually away from the depth of, like, we're not in the middle of this thick spiral arm, right? If you're in this spiral arm, we probably wouldn't be here because you have a lot of gas, dust, a lot of interactions from all those stars, right? I mean, this doesn't do it justice. This is more of a cartoon here. And I think if I remember the numbers right, I think at the co-rotation radius, I think it's like 230 million years to do a revolution around the solar system, and we're moving like 500,000 miles per hour. Our solar system is. It's something like that. Yeah.
I just want to see if I got this right. I thought the gaseous areas are where more stars are formed. Are you saying that they form in this gaseous area, the parts of the arms, and then they have this tendency to coagulate together with other recently formed stars, and then they might migrate around the galaxy some? Are you saying, is it just purely a numbers game that the stars happen to be in these clusters?
No. So what I'm like on a scale like this, right? We can't really see the individual clusters, but the idea is all stars form from condensation of the gas, right? Now, a lot of the gas exists because it coagulates because of these density perturbation conglomerations. They're like density waves. I don't know if you guys like phase velocity and regular velocity, like in plasma physics, maybe. It's not a physical object moving at a certain rate. It's the way I don't know how to explain it. It's sort of like the way it's like a pressure wave in a sense. And so what's happening is there's gas in between the arms and there's gas in the arms, but this pressure wave pushes through and it kind of bunches up the cloud and can compress it. And when that happens, that can kick off star formation. And that's why we see star formation usually in the spiral arms, right?
But you were saying that by numbers, there's more stars in the cluster, but the clusters don't have any gas. So it's like,
yeah, no, they have gas. Yeah, no, they have gas. So right now, like in the Milky Way, today we can see about 160. Let's say, I think the number's 160. Let's call it 160. There's 160 clusters, but these have already formed, right? The Milky Way has been around for more than 9 billion years, probably. So yeah, you have clusters. There's gas in clusters, right? So you can form individual stars, but because there's gravitational interactions, right? They're always popped out and they break apart over long periods of time. They're moving along rotating around the core of the galaxy. And so they can kind of merge through gravity and they combine and, a lot of them bunch up together in the arms along with other dust areas. So it's kind of I think it's a mix of both of those. But the clusters themselves, the ones that are in the plane of the Milky Way, are rotating also, right? So I'm not sure if I answered that or not. We can talk more, but yeah, sure if you guys have any more questions.
Okay.
Yeah, Doug.
I got a question, related to Al's question.
Yeah.
So I've never heard a good explanation for this. So stars form out of open clusters, right? But then once they form, the stars disperse from each other rather than being gravitationally bound, come together.
Yeah.
Open clusters seem to disperse. Do you have a good explanation why they disperse instead of come together?
No, not really.
Yeah, nobody-
I think,
nobody
I
seems to
think,
know.
well, I mean, so open clusters they're the ones that, like the globular clusters form like balls, right? All the other, when it's more spread out, that's open. So a lot, I don't know if they all break apart, but I think a lot of them end up that way. And I think individual stars, it really just depends on the motion and what's near them that can kick stars and break them apart, right? If you have like a spiral arm sweeping through a cluster, right, that's going to completely spread everything apart, probably. I mean, it really depends on what location you're talking about, but I mean, it's not that unreasonable to think that they're perturbed and spread apart just from something moving by it. But I don't know if there's a good answer for that, actually.
Yeah,
It's a good question.
I've never heard a good answer for that.
Well,
Yeah.
think about it this way. You know how the experiments where you actually put on kind of like a liquid that's kind of like an oil where you put different colors and then you start spinning something around it. You have balls of colors, but once you start spinning, they kind of spread a little bit out. I think that's kind of what's fun. That's kind of what's happening, especially when we have pulses on our galaxy. As it's rotating, it actually starts to make it turn and spread out in the orientation. It's all moving as a group all together.
So video, you're saying we're just a big blob of grease in that.
Good colors.
Effectively.
It's more like the Brownian motion of fluids, where you get all the stars to act as gas particles. And if they gather up, their gravitational fields will create density waves that can actually disperse those open star clusters if they're in the spiral arms versus being in the spaces in between. Whereas the globular clusters are sort of partitioning out of the original dust,
Yeah.
the disk of dust and gas. And as that collapses in and spins, and depends how much mass it has, and angular momentum, where it turns into the spiral versus elliptical,
Yeah.
those globulars are going to be partitioned. Whereas you got the open star clusters as they form out of the spiral arms. And you got lumps of stars over the place in these huge stellar associations. It's just going to be a tug of war. The open star clusters are going to lose that.
Okay, I hadn't thought about that.
Did your image earlier not show though that most of those clusters, except for not in the disk, but above below?
Well, the one, they're easier to see because they stand out, but I don't even know if that was to scale, but that, like I said, I think the numbers between 155 and 160, and that wasn't showing that many of them. I don't know can I go back on this? Oh yeah, here we go.
Globulars can be disrupted as
Yeah.
they go through the Milky Way. And they do, they have
Yeah.
to collide and form blue stragglers, and there's the occasional planetary nebula that forms, but that's like once every several hundred million years.
Yeah. So I don't really think this is to scale. It's approximate, right? I mean, I'd have to go kind of research. I pulled this off an ESA site, but what we're not seeing, there's a lot still in the plane here too, but they can exist in the halo.
So they say a lot of the globular clusters is around the halo and the open clusters are around the disk.
Yeah, I've heard that too. Yeah.
Forming the disk, and the globulars are in these sort of high elliptical, highly inclined orbits. They just circle around the central bulge in the way they form. And so they're tightly around the bulge, and they go around those oil patterns like the stars in the globular cluster.
Yeah.
Whereas the later generations of stars, because of that angular momentum as the disk collapse to form the galactic plane, they're naturally going to form inside that galactic plane with the later generations of clusters.
Yeah. All right.
Guys, we
Well,
better
thank you.
move on. Brandon more about this mod pizza tonight.
If you ever go to a star party with Brandon at nighttime, all these people want to stand around and talk to him. It's really annoying. But everybody there at the star party seems to come down and want to talk to Brandon in the middle of the night, all night long about stuff like this. Yes, he has a lot to tell people. Okay, Ron, tell us about the DVD library.
Yeah, what you see on the screen up there, the ones on the left are the great courses. They're over 10 hours long. The ones on the right are they're infinite cosmos. They're produced by Astronomy Magazine. And so the majority of what we have, about 80%, are
and they're about 45 minutes long. And of course, great courses are all over the And we also have planispheres, sky atlases. We don't no longer have a DVD player. We have those that just give you with on the disc.
Excellent. So during the break, you guys can go up and get yourself an astronomy DVD from Ron from the DVD library. Okay, so after the meeting, we're gonna have the meeting. After the meeting at Mod Pizza, you zoop up Millbrook North. You take a left on Clear City Boulevard, and right in front of HEB, there's Mod Pizza. We'll get together there and talk about astronomy and other topics. We're gonna take a 10-minute break, and then we'll come back for the second half of our meeting. 10 minutes.
Good talking.
Yeah, it's all out there. Yeah.
astronomy and art.
The second half of our meeting is starting. They don't believe me, do they?
Oh, yeah.
Okay, we are going to start the second half of our meeting. You guys are not listening to me. The second half of our meeting is starting. The second half of our meeting is starting. Okay. We're mostly there. Okay, second half of our meeting. Okay, now I know you guys would be terribly disappointed if I didn't have at least something about radio astronomy. So here it is. Okay, focus. It's not just for optical telescopes. Okay, so when we focus a telescope, an optical telescope, we have a little star and we try to make it small and we defocus it and it gets big, turns into a blob. Well, that's not just for optical telescopes, also for radio telescopes. But the way we focus a radio telescope is by moving the feed antenna back and forth until it's in the focus position of the dish, right? Now, for those of you, there's some of us in the club that have actually purchased this nano VNA gadget, and the purpose of this talk is to tell you, you can actually focus your radio telescope with this nano VNA, which I was surprised you can do that. You can actually hook up the transmitter side, which is this little jack here, to your transmit antenna, which is this antenna in my case. You hook up the receiver over here to this side, and you can move your secondary antenna, your feed antenna back and forth until you get the maximum signal. Same setting you'd use if you're testing a cable. And you can actually focus this thing. This, for example, this is a loop antenna, and you can see it's kind of like on a dowel rodish type thing. You can move this back and forth until you get the maximum signal if that's your focus point. So in this case, with this particular radio telescope, I was actually able to gain 5 dB just by moving this thing back and forth. From my previous position to the new one, about 2 inches, I got about 5 dB gain by doing this. Yeah. And here's a picture of a sun crossing out of focus and in focus. So remember the first one I showed you with the optical telescope, you get a tiny star, you get the blobby star. Well, the top one is the sun crossing, there's the sun going across, and you see it's wider, right? Blobbier, and then the one at the bottom is with it focused, and the sun crossing is actually narrower. And it turns out the bottom one is actually showing the theoretical expected resolution of this radio telescope. So it actually is performing the way I want it to when the thing is actually focused. So there you go. You can focus your radio telescope with a little cheap nano VNA. And I know several people in our club have those, and that's why I bring this up. All right, now next up, we have Reed, who's going to tell us about the C-Star S50 telescope.
Here it is. Let's see, how do I make this go? Enter? Okay, this is it. It's $500. You get everything you need in the box. It's very simple. If I can do it, anybody can. It takes some pretty good pictures. It's the big question on the internet is it a telescope or is it a toy? To me, it's a telescope. To Doug, it's probably a toy. It depends on how good you are at astrophotography right now. All your pictures come out right on your cell phone or your tablet right away. There's no polar alignment or anything. You set it up, you spin it around a couple times to get the compass oriented. You level the telescope, and yeah, it uses plate solving. You just turn it on, it goes up, figures out where it is. Come to find out, it's an alt-az mount. Learn something new here. It's not equatorial. That means that star rotation or the rotation, you'll get rotation problems if you have long exposures. So it's usually limited to about 10 to 30 seconds. And yeah, there's lots of 3D things that you can get for it, pretty cheap. Triplet APO, 50 millimeter, Bluetooth, Wi-Fi. Yeah, again, it hooks right into your phone or tablet. Says it's got a 6-hour battery. I haven't done that yet. It's got a built-in light pollution filter that you can turn on and off, which is really handy. It comes with a solar filter. And yeah, it works real well. A little less than 6 pounds. And the pictures it takes, it automatically stacks them as you go along. It's really kind of neat. Again, summary, it's fun and easy. Took it to a star party. Everybody seemed interested in looking at it and looking at their phones. Pictures aren't too bad. Again, already stacked and semi-processed. Yeah, that's a picture that I got from Doug's website. Stole it. Yeah, sorry.
That's one of my pictures.
It says Holland Observatory on it.
Yeah.
Terrible. What did you do to it?
Yeah, I was really disappointed in that one. Yeah. But again, I brought the Sea Star with me tonight. If anybody wants to see it and see what comes with it, please feel free to come up. I'll leave it up here until we leave. And again, hopefully nobody has any questions because I really don't have any answers. But yeah, thank you very much.
Okay, that's the first time anyone ever said, please don't ask me any questions.
You know, the Sea Star thing is kind of interesting. There's at least 3 or 4 people in our club that have one of these, so it's becoming very popular. In fact, Paul's going to do a talk next month about his experience with Sea Star also. And last month or 2 months ago, Ken Lester, we had a video time lapse of the eclipse that he had done with the Sea Star. So becoming very popular. Okay, next up we got Dan with the United Space School.
Yeah, this is a project dear to my heart. It was started by Mr. George Abbey, who was the JSC director for a number of years, and is considered the father of our human space program. Now, George put together this thing when he retired. We bring 50 kids from 25 countries to this area for 2 weeks. And those kids are brilliant. I mean, I remember I was hosting one. She was using the VLA, 18-year-old. Manipulated the VLA, that blew me away. And this young woman was, we are still in touch. This young woman is continuing her studies and will probably end up as a top cosmologist today. So we have wonderful kids who come from 2 weeks. We bring them to JSC, we bring them to UHCL, where most of the classes are held. The faculty is volunteers like me. And in 2 weeks, we put together a mission to Mars. Those kids are very impressive. So if you happen to have a free available bedroom, that is something you might consider. That is a fantastic experience. Every single family that have gone through it is raving about it. And we keep in touch with parents on the other side. Now, if you have kids, young enough to have kids that age, then it's wonderful because the parents on the other side of the parent very probably will invite your kid in return. And that creates wonderful exchange and great friendships. And I have so many invitations to go all over the place. Now I'm sorry, but I traveled so much when I was really in work that it's not fun anymore. So, but it would be cool to go to the Southern Hemisphere and observe there. And we have quite a few of those kids. So if you're interested, I have a couple of brochures with me that I left over there. And could you please read me of those old SNTs? I have a bunch of them. I got after a friend died and he gave me a truckload of these and I cannot get rid of them fast enough. They will not let me carry that in the nursing home. So I've got to get rid of them. All right, I'm glad to get rid of him. Okay, that's it. Thank you.
All right. So Dan, I had your slides in here. Did you not want to use those, I guess?
Oh, yeah, sure.
Okay, they're there. There's Dan's slides. There's slide number 1. Be a host family, July 14th through 29th, right? You see Dan?
You're doing a good job, man.
Yeah, there it is. Second slide. Why become host family? Because it's wonderful. Go see Dan. Be cool. All righty. Okie-Tex 5. The purpose of this short presentation, members minute, is to let you guys know that 5 of us are talking about going to Okie-Tex Star Party this year. So I want to let everybody know about that in case any of you have an interest in going. At least 5 of us are going. And if more people decide they're going, maybe next month it'll be the Okie-Tex 7 or Okie-Tex 8. Who knows? So Okie-Tex, it's going to be September 27th through October 5th of this year. And where's Okie-Tex? It's way up there in the panhandle of Oklahoma, about 12 hours, 7 minutes from here, UH Clear Lake. Most of us, drive up most of the way the first day, and then stay somewhere and then get up and then drive the rest of the way the next day because the way Okie-Tex is, spaces kind of get filled up rather quickly. The good spaces do. So you kind of want to get in there early when they first open. Let's see, there's 5 of us going. It's held at Camp Billy Joe. The skies are really dark. It's, if you look on the clear sky clock, there's kind of like 2 levels of Bortle 2. This is actually the darker of the 2 levels of Bortle 2 there at Okie-Tex. It's kind of down in the canyon. So a lot of times when you go to star parties, all along the horizon there's annoying glow. But at Okie-Tex, you don't have that because you're down a canyon. So the canyon kind of blocks the horizon. So you only see dark skies, which is a good thing. There's about 400 people that come to this star party. So it's not as big as the old Texas Star Party used to be, but it's bigger than the El Dorado Star Party. And they have absolutely the best door prizes of any star party you'll ever go to your entire life. So I won a camera last year. So this is what it looks like. That's a couple of observing fields down there. There's some buildings over to the left. A bunch of old men out there hanging around with their telescopes. That's all of us. I don't think we made that picture, but we were in there somewhere. But it's a lot of fun. If any of you guys want to go, let us know you're going, and we'll stay in contact so that we all know we're all going to be there. All right, so Star Party news. David wasn't able to make it tonight, but this is our Star Party news, which I'll give real quick. Anyway, the past 2 events were at Hack Winery. They were canceled because of weather. There's a Hack Winery event coming up, Star Party, July 13th, another one on August 16th. And then coming up past that, there's several Hack Winery other events coming up the rest of the year. But then, of course, it's Okie-Tex again. Then there's Observe the Moon Night at the George Observatory, which is like the version of what's left of the astronomy day that we used to do. But I want to draw your attention to this one here. Okay, so Fort McCavett this fall, is going to be a little different than normal. Usually it's only 3 days, but Fort McCavett is going to be 4 nights. Because a lot of people say, well, Fort McCavett, there's not enough nights, but it's going to be 4 nights this time. And it's butted up right next to the El Dorado Star Party. And El Dorado Star Party, as many as you know, is near Fort McCavett. So you can go to Fort McCavett Friday or Thursday through Sunday, and then get up on Monday morning and go over to the El Dorado Star Party and stay there for another week, October 28th to November 2nd. And Fort McCavett is completely free. It's a lot of fun. And Dark Skies, Bortle 2 also there. And so it's going to be a little different. 4 nights this time for all of you guys. Like, I don't see him now. Where'd Al go? Al, where are you? Anyway, he was complaining about Fort McCavett only being 3 nights, but it's going to be 4 nights now. So you can go. All righty. So that's what's going on in Star Party news. There's David's comic for this evening. David, what can I say? He's always got to try to put something funny at the end. Okay, so next month, where is Phil? Everybody's
You
leaving.
went to go look at an altercation.
An altercation?
Altercation.
Oh, occultation.
Yeah.
I thought you said altercation, like a car wreck.
clear skies, one that's visible from its observatory.
Do you know which one it is?
I have no idea.
Okay. Anyway, Phil, who's out looking at occultation, will be our speaker next month, and he's going to tell us about the Solex spectroheliograph. And I've seen it. It's actually a really good presentation. So that's going to be a good one. All righty. That is it for our normal meeting, but we're going to do door prizes now. And who's got the door prize bucket? Because I don't have it. Okay, anybody not get a door prize ticket? Anybody? Okay, I'm showing hands. If you don't have a door prize ticket, you're gonna be really disappointed when you see these. Okay. Don't get your hopes up, they're not that great. All righty. 3805. 3805. Anybody got 3805? No? Probably Phil. Okay, next one. 3786. 3786. You gotta be kidding me. Do I have the tickets from last month or something? All right. 3792. All right, come on down here. Woo-hoo, finally, I got one. Okay, I have STS-93 launch and landing pictures. I have a moon map. Thanks to Austin, it's the Austin fan club there. I had these Axiom patches, which is really cool. Axiom patches, right? I got
So on patch.
yes. You like that?
Yeah, why not?
Sure. Okay. Great.
Thank you.
Wonderful. There's one. Oh, I corrected. I didn't show you the best one. Too bad. All right. Next one. Oh, you want to see the other one? Come here. The other thing is I actually have some I love radio astronomy socks. You probably want the patch better, right?
Right.
Okay, go ahead. Just keep the patch.
Okay.
All right. 3801. All right, Chris. Okay, Chris. Now I got the I love radio astronomy socks. I got the moon map.
They're not big enough for me.
I got MTS-93 crew pictures. I got an Axiom patch thanks to Austin. I've got some patents. Look at this. A patent of a dome.
Nothing I would take. The DVD.
The DVD. All right. Good go, Chris. Chris used to be our president.
Long time.
Yes, and he's so relieved he's not down here now. All right. Last one. 3780. 3780. You got it. Come on, Max. Woo-hoo! Okay, Max, I got patents of some kind of contraption. I don't know what that is. I have a moon map. I got I love radio astronomy socks. I've got an Axiom patch. Thanks to Austin.
What is it?
Look at this. I got 3 of these. Some kind of patents.
That's it. I'll take this.
You want that one?
I'll take this.
You take it. All right, Max. Good. All righty. Okay, that's it for our meeting. See you guys at Mod Pizza here in a few minutes. Thank you for coming. Woo-hoo. I can't believe I didn't want my socks. Are you relieved I didn't auction off your fellowship?
Oh, well, yeah, me and the son are, yeah.
Hey, that's a good friend.